Okay, so welcome back to another lecture on Introduction to Soft Matter. Last week we had stepped into the lab and we did experiments in the lab with polymer solutions, and we got an intuitive, what we had been building an intuitive idea for, and theoretical ideas in the class. We were able to actually see it in action. Now, in this particular class, I'd like to discuss some of the important issues related to the lab experiments, right? Now, when we went into the lab, we did an experiment with what we call a polymer solution. Okay? It's an important state of existence of the polymer, where the polymer exists in a binary solution, right, as a binary mixture, because we added powder to water, and that's why we call it binary. Is this there's a solvent in a sense, the water, and there's the polymer. So this is one mode in which, or one state in which you can find polymers. You can obviously also find polymers in their original state, where they're only polymer molecules and nothing else. So with regards to that, let us clarify some of the things that we saw in the lab and how they might affect experimental results, right? So once again, as I said, we looked at polymer solutions, and polymers can exist in different states, and the polymer solution is basically a binary liquid mixture. Okay? So a polymer solution is usually meant to refer to a binary mixture or a binary liquid mixture where the long chain polymer molecules are surrounded by smaller and hence less massive solvent molecules. Now, such polymer solutions can exist in different states. The moment I am saying a binary liquid mixture, so obviously binary liquid mixture is the simplest type of polymer solution. You can have other more complicated forms, but for the sake of simplicity, that's what we did in the lab. We looked at a binary liquid mixture. So let us keep our attention focused to that. So the moment I say a binary liquid mixture, it should come to your mind that you can have, so basically you have a certain concentration of the polymer in another solvent, and that concentration can be varied, right? Because in the lab, what did we do? We took a powder and then we dissolved it in water. The amount of powder that we dissolved in a certain amount of volume of liquid or water, that is a parameter that we can control. So we can decide how much polymer we want to mix in the solvent, right? So depending on this concentration, so in a binary solution, one of the most obvious parameters is the concentration of the solution, right, or the mixture. So the concentration will start to decide how the polymer solution really behaves. Now, depending on the concentration of the polymer in the solvent, there are many different type of states of a polymer solution that are possible, okay? And they differ from each other in important physical respects. So let us see what they are. Okay? So polymer solutions can exist in different states. Okay, so I'll make a few boxes and 3. There are 5 different ones that we will consider today. So, I will make 2 more. Okay. So, the first and the simplest possible system is where you have, this is let us say a polymer molecule. It exists as a, it is not exactly a globule, but it is neither all straightened out. It is a polymer coil. So, the polymer chain exists in a coiled state, right. So, this is a polymer molecule in blue that I have drawn. So, let us say there is another polymer molecule somewhere else, and we have a few more, okay. And then interspersed here are the solvent molecules. I am drawing them as dots because they are smaller and hence they are less massive, right. So, this refers to, this is solvent molecule, and this is a polymer coil. Under normal conditions, the polymer has to exist in a coiled state because of Brownian motion, right. We have talked about that before. So, this is also what is known as a dilute solution. This is, and it is called dilute, and we will write it down in a moment. The reason it is called dilute, this image should give you an idea of why, right. So, sorry, okay, like that. The reason we call this dilute is because the polymer molecules exist by themselves and they are so less in number that they do not interact with each other. Okay. So, their molecules are separated by large distances and they hardly interact. Obviously, this is not a static picture. Brownian motion will eventually make one interact with the other one. But the idea is that the number of polymer molecules is small enough that the chances of encounter are very small. So, this immediately tells us that there should be another state where they are larger in number than the dilute case, and where the polymer molecules are just about to start interacting, right. So, if I draw a polymer molecule in a state like this, this is another one. So, now you see I am drawing larger number of polymer molecules. Okay. And this is such that this polymer coil has a certain volume, and so does the neighboring one, and so does the neighboring one. And this sphere that I am drawing is the effective volume of the coil, and you can see that the effective volume is just such that the coils are not really overlapping, but they are just about to do that. Okay. So, I am not drawing all of them, and obviously there are solvent molecules. So, the solvent molecules are so small that they are just around in the solution space. So, later on I am just going to leave out the solvent molecules because we know that they are really much less massive than the polymer molecules. So, this is also what is known as a intermediate stage or intermediate regime. So, the next regime is called semi-dilute. Here the polymer chains are large enough in number that different polymer chains start to interact. Okay. This is another polymer chain, and they are large in number such that the chains are just about to, the concentration is such that the chains have just about started overlapping. This is a very intuitive description, right, at this moment. We will make it quantitative in a second, but let us first understand it from an intuitive perspective. So, obviously, the idea here is to keep on increasing the polymer concentration and decrease the solvent concentration. So, you can reach another state which is called the concentrated state if you keep on increasing the amount of polymer. And finally, this one more which is called liquid crystalline. In this concentrated case, you have a much larger number of polymer molecules, but they are still in a situation where they are not really, they are still scattered in an isotropic way. In the liquid crystalline, certain order can start to emerge in the system. Okay. So, the polymer molecules they are very large in number, but there is some amount of anisotropy that has started to come about. So, just to write it down. So, the first one was the dilute case. So, dilute regime. In this regime, macromolecules are separated by large distances and do not interact significantly. As such, the properties of the solution are governed by the properties of individual macromolecules. Sorry. Are determined by properties of individual macromolecules. Now, just because the solution is in a dilute state does not mean that the polymer does not have an effect. It can still have a very strong effect, but whatever the effect is essentially because, so let us say you subject it to a external stress and the flow starts to occur. Then the flow properties will be governed by as if the polymer molecules, it is the stresses on the individual polymer molecules which will be largely responsible for the behavior of the solution or the response of the solution, right. So, in a sense this is similar to low density gases, okay, where they are not interacting with each other. So, with increasing concentrations, okay, so increasing macromolecule concentrations. So, I am using the word macromolecule and polymer interchangeably here. The polymer chains start to, or the polymer, actually the better word is coils, okay, because they exist in a coiled state. The polymer coils start to overlap and interact. And it becomes much harder to discern the contribution of the individual macromolecules. Now, when you take a solution like that, let us say a semi-dilute solution, and you subject that to an external stress, the solution will behave in a way as if the polymer molecules are obviously individually stressed, but the polymer interactions will also start taking place. Okay. So, it is like information is going to be passed from one polymer to its neighbor and its friend. It will tell its friend how what stresses it is feeling, and his friend will also end up feeling some stress, right. So, that is how this interaction now that starts to become important in that case. And one of the final states that we drew is called the liquid crystalline state. In this particular case, obviously the polymer concentration is very, very high now, but a liquid crystalline regime, so a liquid crystalline polymer is an example of anisotropic anisotropic polymeric liquid. We are not going to go into how this anisotropy can develop, but it will suffice to say here that this anisotropy can also develop spontaneously under certain conditions. Okay. Okay. So, till now our discussion has been more or less intuitive and qualitative, right, but we want to make it quantitative now. So, let us discuss some of the important numbers that we can associate with these kind of systems. Before we do that, I just wanted to recall that we have discussed what the effective radius of a polymer coil is, right, and I hope you remember. So, we had discussed a few lectures back that the effective radius for, so R effective, the effective radius for a polymer, with n segments, where the length of each segment is a root over of n, right. So, the volume of such a polymer, the coiled polymer, so the volume or the effective volume, okay, so I will just write V for volume. Okay. So, hence V effective, where V stands for volume, is now going to be 4 by 3 pi R effective cube, which is equal to 4 by 3 pi A cube n to the power 3 by 2, which implies that V effective, if we drop this number 4 by 3 into pi, then this scales as A cube n to the power 3 by 2. So, now let us figure out where, so let us define concentration. Okay. So, let us define concentration C as the number of segments per unit volume. Okay. Now, I am just going to quickly go back to the 5 states that we discussed. Okay. So, in the intermediate regime, you have a situation where the polymer coils are in such a state that each of them is occupying a certain effective volume, but the effective volume of each is such that the volumes are basically touching each other, right. So, it is almost as if there are n number of, so each polymer has, let us say this is a monodisperse polymer. So, each polymer molecule is exactly has n number of segments. So, in this case, if this is a state which we would define as the critical state, okay, or where the concentration is of a critical nature, then this C critical is such that, so C critical is such that there are n segments per volume or for the effective volume of a polymer coil. So, this gives us, this is n. We just saw that this effective volume scales as 3 by 2. So, this scales as a to the power minus 3 n to the power minus half. This is a very important equation, because it gives you the dependence of C star on n. Usually for polymers, if there are carbon-carbon, if the backbone of the polymer is carbon chain, then you do not have much control over the size of the length segment, but it is n which is usually varied in the polymer. So, this gives you a very nice explicit dependence of C star on n. So, now if a overall concentration, so now if overall concentration C of a polymer is such that C is less than C star, then we can say that the individual polymer coils hardly overlap, that individual polymer coils hardly overlap. What does this mean? This means that in the lingo of the previous states that we had discussed, that this will belong to the dilute state or the dilute regime, right. So, if I had to write down, I am just going to erase this, because I am going to write down some of the expressions. So, for this particular case, the dilute case, your concentration C is such that C is less than C star. Obviously, here I would have to write that the overall concentration is such that, just a second, or the overall concentration is such that C is of the same order as C star. So, C star corresponds to this threshold regime or the intermediate regime. Now, there is a slight problem with using C as a important parameter, and that is it has units. So, it is if you see how we have defined it, is number of segments per unit volume. So, in such kind of a case, another important parameter that becomes very useful is a quantity called phi. Okay. So, phi will define it as the volume fraction of the polymer in the solution. Okay. So, another important quantifier is a parameter called volume fraction, or parameter called, just say, let us say phi, which is the volume fraction of the polymer in solution of volume fraction of the polymer in solution. Now, how obviously the moment we are associating a number which are associating a quantity, we have to tell how do you calculate it, right. So, let small v be the volume of a single element and C be the concentration. Then obviously, phi is related to C and V by phi equal to C V. Right. So, what does this imply? So, when you have phi equal to 1, you will have a situation where there are no solvent molecules, there will only be polymer molecules. So, that is also called a polymer melt, by the way. Okay. So, let us try to estimate this number. Okay. So, let us say that a single, so we have already said that, so when we are considering a single segment, we said that this distance was A. Right. So, it also has some effective diameter, and let us call this diameter D. Right. This is a single segment of the polymer. So, then your V scales as A times D square. This is the volume of this cylinder without that pi by 4. Right. So, I am dropping that same number over there. So, now phi star is the critical volume fraction is a volume fraction such when your concentration is also critical. So, phi star should be equal to C star into V, right. So, we have already seen how did C star vary? C star varied as a to the power minus 3 n to the power minus half. So, a to the power minus 3 n to the power minus half. And what is V? V is A into D square. Right. So, my phi star is varies as D by A square n to the power minus half. Right. Now, this D by A is a molecular scale information, right. This is in some senses looks like almost an aspect ratio. So, this is an important number, but it is usually sort of fixed in most cases. Now, D can range from in practice it can range from anywhere from 1 to 50. For example, DNA molecules can have D by A of the higher on the higher side. Okay. But for the time being, let us just imagine that D by A is equal to 1, then what happens? So, if D by A is equal to 1 and so I am trying to take a very specific scenario and n equal to let us say 10 to the power 4. So, I am taking a polymer such that on the molecular scale this D by A comes out to be almost 1 or 1 and it has 10 to the power 4 segments. Okay. So, what does my phi star come out to? 10 to the power minus 2. What does this mean? This means that polymers, okay, so this is an example. Okay. So, here let us say, okay, so just a second. Okay. So, this is an example problem. Okay. So, here this implies that in such a situation the polymer chains will start to interact when the polymer concentration is only 1%. In this case, polymers can start interacting only at 1% concentration or volume fraction. This is quite interesting because typically we tend to think that phi or 1% is a small number, but for polymers 1% can be very, very large. right? They can be extremely significant, which is why for the kind of polymers that we were using, at 1% you can actually end up getting very significant viscoelasticity. Okay. So, we should not bear the notion that for polymers dilute means 1% can be dilute, okay, but 1% need not be dilute. So, this is an important issue here, which is why when we had discussed this intuitively or just on a qualitative basis, then it does not really tell us at what scale or what is the real concentration at which these states are achieved. But now that we have gone through this quantitative process, we know that this kind of a state or these states can be achieved at, or the intermediate state for example can be achieved at very low concentrations also. So, obviously the intermediate the semi dilute situation will occur when C will be greater than C star, and as C starts to tend towards 1, you will start getting the concentrated, and you can also get the liquid crystalline under different conditions, but here C is just slightly greater than C star, and as C starts tending to 1, you will end up getting the concentrated regime. Okay. So, basically for polymer chains, the takeaway notion or the takeaway lesson is that when n is much greater than 1, there will exist many states where by varying the volume fraction you can achieve all these different states, and this argument will not hold if n is very small. Okay. So, we must remember that this entire calculation holds only when n is much greater than 1, and what is the reason for that is because in the beginning itself we took the idea that the polymer exists as a coil. So, that coil structure can only exist if n is much greater than 1, right. Okay. So, this I hope sort of clarifies to you the exercise that we took in the laboratory, where we looked at a binary solution of polymers, and that is why we did this entire exercise of going through figuring out C star and phi star. Now, another thing that we did not do much in the lab is when you do experiments, there are important conditioning exercises that one has to do. That is something that we did not do. For example, for creep compliance tests, it is often that a standard conditioning operation is done, where the load is applied on a fluid or a material and it is unloaded, and this is done repeatedly, and usually the maximum possible load is applied, and then it is kept unloaded for about even 10 times the time of the loading situation, and this is done repeatedly, and the reason it is done is so that the system should not have any long term memory and that it loses long term memory, so that the results can be treated as if the system did not have long term memory and it is only reacting to the stresses during the duration of the said experiment. Okay. So, those are things that you would learn if you take a very detailed course on rheology. That is why this is an introductory course, as we have already discussed in the very beginning of the course. So, those are things that you would probably encounter and understand and learn much better when you take up advanced courses. Okay. So, we will end today's lecture here, and I will see you in the next class. Okay. Thank you.